Welcome to our channel dedicated to the world of ground-penetrating data interpretation using the Wave software. Whether you're a beginner or looking to enhance your skills, you'll find valuable insights and practical tips to help you unlock the full potential of GPR technology. In today's episode, we're diving into the seemingly simple topic of GPR survey without GPS. Just a wheel and tape. Let's imagine a naturally shaped landscape with a few objects lying just beneath the surface. The topic of deeper object placements is a whole different story, which I'll cover in future episodes. The dimensions of our area are 10 by 21 meters, so the length of the profiles will be 21 meters. We're starting the data acquisition using a measuring wheel, and we'll wrap up at the point where the measured distance with the wheel is 21 meters, right? Well, not exactly. To be honest, I couldn't believe that someone would trust a measurement wheel to that extent. Essentially, a measuring wheel can provide reasonably accurate results only for short measurements taken on flat surfaces, like asphalt roads. Longer stretches will also carry some error, but we'll discuss that in future episodes. If we take a measurement along a taut measuring tape, we'll obtain a longer profile. The difference, of course, comes from the fact that the terrain is rarely flat as a table, so the measured distance will generally be greater than tape measurements. Therefore, we should rather refer to this as the plane length. If we flatten the terrain curvature now, we'll see how significantly the locations of the detected objects change. The farther we move from the start of the profile, the greater the measurement error becomes. The red dots represent the actual locations of the objects, while the blue ones are derived from our measurements. If we leave these measurements uncorrected, we can be certain that we'll encounter a measurement error that increases with distance. If we use the measurement from the first example, where we finish the profile relying on the reading from the measuring wheel, we'll achieve a similar effect. Only this time, the profile will simply be shorter. The localization errors will remain unchanged. One of the simplest techniques for correcting measurement errors is to rescale the measured length of the profile to match the length obtained from tape measurements. To demonstrate how this correction works in the Wave software, I've loaded the files and placed them in the workspace. You can see that each of the profiles has a slightly different length. Let's select the one that measures 21.7 meters and choose the Edit Marks and Length option from the right-click menu. We're setting the selected profile length to 21 meters. Resampling will either change the number of tracks or their spacing. In this case, I've chosen to maintain the same distance between the tracks. The length of our profile has been adjusted. We can repeat this process for all profiles in the selected area. This method, however, is not ideal since the change in topography is random, whereas linear correction is consistent. This results in accurate object localization only at the beginning and end of the profile. Unfortunately, the measurement error increases towards the middle of the profile. The only method that will ensure perfect correction is the use of distance marks applied at equal, ideally minimal distances during acquisition. In this sample profile, we can see 20 distance marks registered during the acquisition, spaced 1 meter apart according to measurements taken along the taut tape measure. The path of the measuring wheel varies, which is why the distances between the marks are not equal. This is exactly what I intend to correct now. By selecting the same option as before, I open a window that displays a list of all the marks. We set an equal distance of 1 meter between the marks, and just like before, we choose one of the parameters for resampling. Voila, all the distances between the markers are now equal. As you can see here, this method provides the most accurate representation of object placement possible. Essentially, it's the same linear correction we applied to the entire profile. However, the small distance involved has resulted in minimal errors. The smaller the distance between the marks, the smaller the measurement error. You're probably thinking to yourself right now, why bother struggling with this when I can measure so much easier and even more accurately using GPS? Really? If you want to find out if that's actually the case, click follow, give a like, and stay tuned for future episodes.